Good morning, everyone. Thank you very much for joining us today. My name is Sagar Desarda, and I'm our tech leader for United States for AWS Edge Networking Services. So today I'm going to share 7 design patterns that'll help you increase the availability of your online applications using AWS Edge services. And as you would agree, it is impossible to completely rule out the possibility of a downtime. However, you can greatly reduce the probability of service disruption by building highly available applications. And I plan to share some of the design principles on which we've built our services. So, and a quick level set that this is a 300 level session. So I assume you have some working experience with our services like CloudFront, AWS WAF, Shield, Route 53, etc. And our agenda for today is I'll talk about why availability matters and what does it depend on. I'll share some of the design principles on which we've built our services, and you can potentially use those to build highly available applications yourself. And I'll go over the 7 design principles using these Edge services for you to build highly available applications yourself. So when your network or applications unexpectedly fail or crash, the downtime can have a direct impact on your bottom line and ongoing business operations. And the monetary losses vary when you consider the revenue, industry, the actual duration of the outage, the number of people impacted, the time of the day, etc. So when you look at how do I improve the availability of the application, it is important to understand what does the availability depend on. So I'll talk about, it depends on 2 things. I'll talk about how platform infrastructure like AWS we've built for you plays a major role in achieving those high availability SLAs. And the second is how you architect your application will also determine how available your application is. So talking about platform architecture, the AWS Global Cloud Infrastructure is the most extensive, reliable, and secure cloud computing environment with the highest quality global network performance that's available today. Every component is designed and built for redundancy and reliability, from regions to networking links to load balancers to firmware. And talking about our footprint from an Edge services standpoint, CloudFront now has more than 300 Edge locations across 47 countries. We are growing at a very aggressive rate, and all these POPs are hosted on AWS Backbone, which is privately managed by AWS. This provides a better network quality and isolation from internet issues. And AWS has unmatched experience, maturity, reliability, security, and performance. And as our CEO says, there is no compression algorithm for experience. And that's because you cannot learn certain lessons until you get to different milestones in scale. And we've been building our network for more than 15 years. And we've used that experience to make our services resilient, specifically Edge services that I'm going to talk about today. And I'll share some of the principles that we leverage to do so. The first one is the pattern of food testing. That's essentially validating changes to state before they're delivered to your production applications. So most of you must be familiar, like back in those days when there used to be kings and they would have these vile enemies that wanted to poison them. So imagine a king is sitting in his dining hall, he has all this food coming down, and he says, wait a minute, I'm not going to eat it yet. And he probably called the squire, like, you squire, come here and taste this for me. I'm going to watch you eat it and see that you don't kneel over. And if you don't, then I'll eat it. I don't think this will work well in practice, as not all poisons may be that fast acting. But in the software world, this is very much applicable. Our applications do react quickly to poisonous inputs. So the idea of food testing is applicable to the category of software bugs you are trying to prevent from these poisonous code paths from being tripped. The next one is adopting a CI/CD approach as a way to reduce the blast radius of the unintended code changes. So I'm sure you're all familiar with the good engineering design principles of doing code reviews and tests and running CI/CD and wave deployments. So I'm not going to get into that. But applying that concept, what we've done in CloudFront is we have this change propagation system where we have these parcel builders who fetch the config from the data store. They put them in S3 buckets. They're put across multiple S3 buckets in multiple regions. And these Edge POPs will then go and fetch these configs. And when we deploy these changes, what we do is striping. So striping essentially is a collection of components in different parts of the system that are isolated from each other when it comes to ingesting the config. So when the changes are being deployed, say you have this one parcel builder, you have one S3 bucket, and a small number of POPs. So if ever there's an issue, you just take out that small number of POPs or small subset of POPs out of service, which is transparent from an end user's perspective, and the customer experience remains uninterrupted. The next one is diversity. So the idea here is to introduce some randomness, basically breaking the monoculture in your application design. And one of the examples that I'll talk through is to explain this is the problem with homogeneous systems. So these platforms were great because everything is derived from the same template, they're on the same platform. I don't have to worry about a version of Linux in one system to say like a version of Solaris in another to a different version of Linux in another system. But there's a problem having homogeneous systems. So here I have 3 servers. The green box represents the root file system of the servers. And in my example, mine is a photo sharing website. So in my day-to-day operations, I could have some configuration updates coming in. They're typically small. They'll take small disk space. But like last week, I had some server crashing issues. So I now have some binary patches also that are running, and I haven't had time to clean them up as yet. And now, one of my users decides to digitize their entire photo collection, and I have petabytes of pictures of cat coming in. And all of this is happening in a very short time. And this results in all of my servers breaking at the same time. So what do we do to solve this problem? So CloudFront does this. We jitter the file system. It's essentially identifying the components that might fill up and providing a jitter or variance across those. So this almost acts as an early warning sign. If you do encounter a scenario where the disk has filled up, we just take that single disk out to investigate what happened. And from an end user's perspective, you will never see a drop in availability. My fourth pattern is shuffle sharding. Shuffle sharding is a core pattern that makes it possible for AWS to deliver cost-effective multi-tenant services that give our customers a single tenant experience. And shuffle sharding is actually more powerful than we initially imagined it to be. So imagine a horizontally scalable system that is made up of 8 workers. And these workers could be your servers or queues or databases, like whatever is the thing that makes your system. And each worker has to be able to handle any request. And this is great from an efficiency and redundancy standpoint because if a worker fails, the other 7 can absorb the work. Now imagine there is a surge in the requests or there's a DDoS attack that happens and that takes out the first worker. Now you have more traffic than usual and you're operating at a slightly reduced capacity. Imagine that the requests continue to increase and this now has a cascading effect. It starts taking out all the other workers and with it now your entire service. So how do we solve this problem? So now say if we divide the fleet into 4 shards of workers, so we can trade efficiency for scope of impact. So in this example, each shard has 2 workers. And now here, if a customer on blue does experience a problem or an attack, the scope is just limited to blue. So with that understanding, let's apply this to our customer traffic. So in this example, I assign the rainbow customer to the first worker and to the 4th worker. So the combination of these 2 workers basically makes up the customer's shuffle shard. And the other customers will go to different virtual shuffle shards with their own mix of 2 workers. So for example, the rose customer is also assigned to the first worker, but then its other worker is the 8th worker. So now imagine that rainbow is experiencing a problem on an attack. Now let's see what happens. So say because of an attack on rainbow, it's taken out the 2 workers, the 1st and the 4th. So for customers, that means that even though the Rose and the Sunflower customers each share a worker with Rainbow, they are not impacted. The Rose can continue to get service from worker 8, and Sunflower can continue to get service from worker 6. So we use shuffle sharding in many AWS services. And for my example, I choose Route 53, where we've decided to arrange our capacity in a total of 2,048 virtual name servers. So these servers are all virtual because they don't correspond to any physical server hosting Route 53. And we can move them around to manage capacity. And we then assign each customer domain to a shuffle shard of 4 virtual name servers. And with those numbers, there are a staggering 730 billion possible shuffle shards. We have so many different shuffle shards that we can assign a unique shuffle shard to each domain. And actually, we go even further to ensure that no customer domain will ever share more than 2 virtual name servers with any other customer domain. And we've gone on to embed shuffle sharding in many of our other systems as well. In addition, we've come up with some refinements such as recursive shuffle sharding, where we shard items at multiple layers, thus isolating our customer's customer. That's basically your customer. And shuffle sharding is enormously adaptable, and it's a smart way to arrange your existing resources. It comes at no additional cost, and it's a great improvement that frugality and economy can drive. And because of this highly available cell architecture with sharding and Anycast, we offer a 100% availability SLA with Route 53. Even with the US East 1 service event that happened in December 2021, Route 53 data plane was functional, and customer applications that relied on Route 53 for routing worked seamlessly. Next, I want to talk about how does the load balancing happen inside a CloudFront POP, and how is CloudFront able to handle the rapid surges in volume effectively. So in a CloudFront POP, we got servers, we have a top-of-the-rack router, and at CloudFront scale, we need a load balancing mechanism that is simple, fast, scalable, and ridiculously cheap. So we enjoy reducing our costs so that we can pass on those savings to our customers, so we don't deploy any high-end hardware load balancers in our POP. So how do we do this? We associate the VIP to a POP, and then we have the router that load balances the servers, and we use ECMP with some sort of hashing to do that. But what happens if host 1 goes out of service unexpectedly? The traffic director will kick in, it detects that host 1's down, and will update the routing table to redirect the traffic to the healthy hosts. But before I jump into what happens next, let me add another piece of complexity. So we have these L4 load balancers that are integrated into each host server. And these load balancers maintain a map of ongoing connections across the POP, so it knows which host is processing which TCP connection. So now let's go back to our example. So now say host 1's down, the L4 load balancer will send the packet to host 3, and your customer's experience remains uninterrupted. And we use gossip protocol, between the L4 load balancers to pass or exchange the host information between them. And just by doing this, we saw a 10x improvement in downtime in CloudFront, and we're not going to stop there. So we've looked at how do we build our cloud infrastructure. Now, let's dive into what you can do to build highly available applications using AWS Edge services, and I'll go over the 7 design patterns that you can leverage to improve the availability of your web applications. So an origin failure need not be a catastrophic event. AWS lets you fail over to a secondary origin so that you can retain the traffic as you enact recovery procedures. So you can do this in a few ways. You can use Route 53 to gracefully handle origin failure events. And once you have the health checks configured on Route 53 on the origin, Route 53 will keep running these health checks to ensure that your origins are functional. Now say there's a request coming in for example.com. Route 53 resolves the IP address of the primary origin, and that's where the traffic is sent to. If the primary is down for some reason, the health checks will detect that, and then Route 53 will just resolve to the IP address of the backup origin. And this will be a seamless experience for the end user. The second way is to set up CloudFront with origin failover that requires scenarios that, where you need high availability. So to get started, you create an origin group with two origins. You have a primary and you have a secondary. If the primary is unavailable or returns certain HTTP status codes that indicate a failure, CloudFront will automatically switch to the secondary origin. So note that with Route 53, the failover happens when the liveness tests detect the failure, and then the DNS flips. And here, the failover happens with the actual error responses for your HTTP traffic. Global Accelerator continuously monitors the health of all available endpoints and instantly begins directing traffic to another available endpoint when it determines that an active endpoint is unhealthy. And it does that within 30 seconds. So this works for any kind of traffic, be it HTTP or non-HTTP. And there are some other use cases also that I want to call out. It could be having greater control over your cross-AZ recovery mechanisms, those rare use cases where you may need the ability to fail over multi-region and to be able to have your application recover in minutes. And while building highly available systems, we focus on preventing loss of service. So I also want us to plan forward on how to recover from that loss of service. And that's where Route 53 Application Recovery Controller, or ARC as we say, comes in. With ARC, you now have the ability to reliably mitigate failures in minutes for even of some of your most largest and most critical applications. And you do so by rerouting the traffic between multiple isolated environments. So improving the application's availability, and this simplifies the recovery of applications across multiple AWS regions or AZs or on-premises. And there are three key capabilities of ARC that I want to talk about. One is the readiness checks. So let's say that the application is a multiplayer tic-tac-toe game, an application that typically needs 99.99% availability or more. And I first deployed this application stack across so that I can fail over across my traffic over. And then these copies of my stacks are deployed across the AWS high availability boundaries such as AZs or AWS regions. In my example, I choose to deploy the application replicas across AWS regions. And then I configure data replication across these independent replicas using DynamoDB global tables. And here, you run readiness audits that can include checking for your capacity. They can look at your config. They could look at your AWS quotas. They could also look at the routing policies depending upon the service. For example, if you want to audit readiness for your EC2 autoscaling across two AZs, you can create a readiness check for that resource. And then you can have those two resource ARNs, one for each autoscaling group. And then ARC will continuously monitor these instance types and the counts in the two groups to make sure that it is scaled equally. The second one is routing controls. So it's a simple on-off switch that's hosted on a cluster that you use to control the routing of the client traffic in and out of cells. So here, the routing controls are durably stored in 5 different AWS locations and can be changed through any one of those regional endpoints. Your routing controls are also hosted on EC2. So the changes to the routing control can happen directly through the Route 53 data plane, which has a 100% availability SLA. And the third one are the safety rules. So you can have the ability to put safeguards in place to avoid unintended consequences. So the assertion rule that you see here essentially creates a safety check to ensure that only one routing control rule is on. So say you're a user that's sending an API command to set the region 1 rerouting to off, and the request goes to the ARC controller cluster, and then from there, the routing chain is initiated and it goes to the control panel. And now, because of that assertion rule that you have, the safety rules are not met. And because of that, the operation is going to fail, and it prevents your application from going down. My next pattern is about static stability. So it's about designing the systems to stay resilient even when some of the dependencies become impaired. And that's what statistically stable design is. The overall system keeps working even when the dependency becomes impaired. So perhaps the system did not see any updated information that the dependency was supposed to have delivered. You can take, for example, like maybe new config, or something's changed in the config, or something's deleted. And however, everything in the system that the system was doing before this dependency became impaired continues to work despite the impaired dependency. And I'll explain with an example how CloudFront is statistically stable. So most AWS services have a control plane which enables you to help create, update, or delete resources, and then you have a data plane, which is the service's core functionality. With CloudFront, the control plane is in US East 1 and allows you to manage your distributions. You can look at reporting, you do invalidations over there. It's designed to provide strongly consistent and durable operations. And then the data plane is distributed worldwide across the global network. And those are your actual CDN servers that process the requests. The static stability of CloudFront can be explained through the Amazon Kinesis event, service event that happened in US East 1 that impacted multiple AWS services in November of 2020. For CloudFront, the control plane was impacted, meaning the time to propagate the changes was taking longer than usual. However, the data plane was running without any issues, serving traffic for your web applications. So expanding on that design pattern, if you're looking to route traffic to origin dynamically based on certain parameters from the incoming request for, say, your experimentation frameworks or your blue-green deployments, you could use Lambda at Edge on origin events to dynamically select the origin. And another advantage of this setup is that you're modularizing your routing logic such that if you do need to change the routing logic, you just make a change to the Lambda code and the rest of your CDN config does not need to be edited. And another variant of the same design is that you can store the routing logic in DynamoDB and let Lambda at Edge fetch it at runtime. And you can probably expand it to DynamoDB global tables for the right use case if you're looking to reduce the latency and improve the availability while achieving global distribution. So the QR code here is linked to a blog post which describes how OutSystems designed a globally distributed serverless request routing service for their multi-tenant architecture. The next pattern is about the ability to execute critical business logic closer to the viewers translates into a faster response time, thereby improving performance and offloading the origin from additional processing. Lambda at Edge has a synchronous event model, and the triggers are one of request or response events. It also helps you serve personalized experiences powered by intelligence at the edge that serve just the right thing to the viewer who is requesting the content. And we launched CloudFront Functions in 2021, which allow our customers to run lightweight JavaScript code at the edge for HTTP transformations and manipulations. It is purpose-built to give our customers the flexibility of a full programming environment with performance, scale, and cost-effectiveness that modern web applications require. It executes JavaScript code natively at the CloudFront's edge locations and scales instantly to millions of requests per second so that our customers do not have to worry about burst or throttling limits. And it runs the code in a memory-safe, dedicated CPU and can process for sub-millisecond latency performance in a highly secure environment. And I would also like to add that CloudFront Functions serve one customer at a time without any system calls or timer routines. And all customer-specific data is flushed between the executions to prevent any sort of memory leaks. And I'll share a Lambda at Edge example that ties in with keeping the site or your application more available. So Waiting Room is a way to provide branded, user-friendly experience to reduce abandonment and protect from site failure when your backend application approaches overload. So during normal circumstances, the user makes a request, the request goes to the origin, the response is served back to the end user. Now, let's consider a slightly different use case. This time, the user makes a request, the origin is under heavy load, and say you have a Lambda edge function that's running, it's set to allow only 50% of the users to the origin. So what happens? You happen to be in the other 50% that gets throttled. The user is sent to the waiting room page, and it remains sticky to the branded experience. The waiting room cookie then will have a timer, and then after a time delta, the user will be put back into the lottery. Assuming that the user is now let in, the request goes to the origin, and then response is served back to the end user. So here, you can choose to set the waiting room cookie on the entire domain and keep the user in the waiting room or on the waiting room page, preventing access to your entire website. Or you can have the cookie specific to a certain directory and to ensure that the user can still navigate through the rest of your website and they have access to it and shop. And so how you do it really depends on you and what your business needs are. And if you're looking to get people into the waiting room page and strictly let them out in a first in, first out basis, like those COVID vaccine registrations, this would be the design that I would recommend. I don't have enough time to get into the design, but the block behind the QR code is a good read, and there is a CloudFormation template for this as well. In our next pattern, I'm going to talk about how do you reduce your attack surface. So web applications are the new perimeter that you're tasked with protecting as they introduce new entry points into your company's infrastructure. So here you got CloudFront, which is accelerating your traffic or application on the internet, and then you have AWS Shield to protect against volumetric types of attacks. And also, CloudFront only accepts traffic from port 80 and 443, and only serves requests that conform to RFC standards. So just by doing this, you're reducing a good number of spurious requests that might otherwise hit your origin directly. And then you have AWS WAF, which is designed to protect your application and mobile assets against sophisticated web and DDoS attacks. And by locking down the access to your data center to just CloudFront, you're able to prevent direct-to-origin attacks. I'm going to talk about a few different ways in which you can lock down the origin access to CloudFront. So say your origin is S3, Object Access Identifiers, or OAIs, allow S3 to uniquely identify a distribution so that the only traffic that is allowed into S3 is from your CloudFront distribution. And once enabled on both CloudFront and the S3 bucket, the bucket no longer needs to be public, and no one can access the S3 bucket without having to go through CloudFront first. We launched AWS Managed Prefix in February of 2022, so you can use the AWS Managed Prefix for CloudFront to limit the inbound HTTP traffic to your AWS origins from the IP addresses that belong to CloudFront's origin-facing servers. And CloudFront keeps the managed prefix list with the IP addresses of the CloudFront's origin-facing servers so that you don't have to maintain the prefix list yourself. My fifth pattern is about how do you defend against DDoS attacks. So distributed denial of service attacks can paralyze even the most well-structured network for days, costing millions of dollars in lost sales, freezing online services, and crippling a company's reputation. And as the attacks get more complex and diverse, organizations face a number of challenges as they look to find broader protection against these DDoS attacks. And DDoS protections built into the AWS infrastructure are always on. They help mitigate the attacks much faster without having to go through external routing or external scrubbing centers, ensuring that your applications do not face aggravated latency. And Shield standard includes basic layer 3, layer 4 level DDoS mitigation, which is more geared towards keeping the AWS infrastructure secure, and all AWS customers get advantage of this by default at no additional cost. Shield Advanced provides additional comprehensive protection against large and sophisticated attacks. So with our always monitoring, we use a number of different techniques to block the vectors on AWS. So we do signature-based detection, we do heuristics-based anomaly detection. So we'll detect anomaly based on attributes such as the client's source IP or source ASN. We'll look at the different traffic levels. We'll look at validated sources to see where is the traffic coming from. We also continuously keep baselining the traffic that's hitting your application, and we do this for us to know what the normal traffic level on your application would look like. And there are quite a few things on here that you might be familiar with, but I'm specifically going to talk about automatic application layer mitigation. So Shield Advanced can now automatically respond to and mitigate layer 7 DDoS. So Shield Advanced identifies the attack signature of an event and automatically creates the WAF rule in a Shield managed rule group to be able to mitigate the attack. And these signatures are validated against the resource historical traffic baseline that I was talking about earlier to be able to minimize the false positives. And then these WAF rules can be deployed either in count mode or block mode. And these rules can also be automatically removed from the rule group after Shield determines that the attack has subsided, or you can choose to leave them in place in case the event recurs. I also want to talk about the rate limiters feature in AWS WAF, which helps prevent your infrastructure from being overwhelmed by requests from users, ensuring availability and reliability of your application for your customers. And it does that by counting the number of requests in a given time period and then applying specified limitations to those requests. So when you set up rate limits, there are 3 types or tiers of rate limits that I would recommend. The first is on the key pages. So if an attacker intends to only hit your sign-in page or payment page, for example, having a specific threshold on that page, since you know what the baseline threshold looks like on the traffic, will help you catch those attacks much faster. For the post request, say with HTTP flood attacks, for example, the attacker would want to overwhelm the origin or your backend server with HTTP requests with the intention to bring it down. And as you know, post requests take maximum amount of resources and require a lot of backend processing. So I recommend setting up a rate limit that monitors the volume of post requests on your application and even on the specific pages. And the third is catch-all, as the name suggests. This would be a catch-all rule to track the overall request of a user on your application. And you can create custom rules to match certain conditions, and you can also customize the WAF response to outsmart the malicious actor. So as an example, you can choose to return HTTP 200 with a fake successful looking response to make the attacker believe that his effort succeeded in hitting the backend. Oops. And when you add new security rules in WAF, always put them in count mode first as a thumb rule under general circumstances. And let's look at an example on how to set the rule to count mode to minimize the false positives. So say you don't want your WAF to trigger on this one subrule, so you put that subrule in count mode, which is looking at the request body size, and then after you do that, you're creating this WAF rule where you're creating a label for that one subrule, and then you put that in a not match, and once you do that, you can then set your overall rule to block mode. And if you're looking to build a security dashboard, this is one of the automated solutions built by AWS. And there's a CloudFormation template for it. You can feed the logs, AWS WAF logs, also into your existing SIEM integration, say with our partners like Splunk or New Relic. And they also have pre-built add-ons where they're able to ingest the WAF logs and make data visualization much easier for you. And this is the last one, protecting the application against the bot traffic. So especially with the pandemic, there's been a huge surge in bot traffic. Bots have targeted new markets. They've tried to hide behind the general traffic surge on the internet. As the pandemic started, the bot activity increased and they were used to hoard sanitizers and face masks and work from home equipments and such. And I'm sure a lot of you would have experienced that the products were out of stock in the stores, and then the same products was sold way above their markup in online marketplaces. And bad bots are also used to scrape pricing and inventory information from large online businesses to undercut their positioning and pricing against these offerings. And then there is this increased fraud with account takeover activities to steal your loyalty points, make unauthorized credit card purchases, wire transfer money from your accounts, etc. Say with, for example, with the 2012 LinkedIn hack, allegedly millions of email password combinations were stolen, and then that list later appeared on the dark web. And the people with malicious intent will purchase that list. They will run that email password combination across several websites or applications with the hope that some of us would have used the same combination and they're able to get in. And before we look to solution or defense against bots, let's dissect the bad bots further. So I classify them into two types. The offensive ones are the ones that don't respect robots.txt. They might at times hammer your website at a very high rate. They might scrape the sections of the site they are marked as do not allow under robots.txt. They may not always care to identify themselves, but then they're also not going to try hard enough to obscure their identity. So you will find a pattern, like be it requests coming from certain geos or IP blocks or ASNs as an example. You could also find the presence of certain request headers in there, or a specific order of request headers as such in the incoming request. The other category are the evasive ones. So they thrive on deception to get around your tiered defenses. They could frequently change their source IPs, ASNs, etc. They could change the header values and make it appear that they're coming from legitimate sources, for example, a Chrome user agent or a Chrome browser. They could selectively run JavaScript. And I've also seen instances where these bots would mimic the human traffic volume pattern. For example, send relatively higher traffic on a bank's website during the day and send much lower traffic at night. Some of the sophisticated bots even send the client telemetry data or behavioral data, such as your device characteristics, device orientation, how hard you're hitting that space bar as an example, to trick those detection systems. And these bots are by far the most difficult to catch, and they cause maximum amount of damage. In Q4 last year, we launched CAPTCHA to help block unwanted bot traffic by requiring the users to successfully complete the challenges before they are let into the application. And earlier this year, we also launched AWS WAF, Account Takeover Prevention, or ATP as we say, to monitor the fraud and control the account takeover attempts. And ATP helps you protect your business and guarantee that the e-commerce transactions are for real humans and not millions of bots that are out there. It rapidly identifies and verifies and prevents credential stuffing attacks that help protect our customers. So holistically looking at your application architecture, you have AWS Shield, which is a managed DDoS protection service, which is always on. It provides automatic inline detection. And then you have AWS WAF that protects against application layer attacks, all of your OS top 10, your rate limits, even the rules to defend against the bots. They all get applied here on layer 7. And then the requests go to CloudFront, which also has integration with Lambda at Edge and CloudFront functions that we spoke about. And the last piece, if it's an API request, CloudFront could hit the API gateway, where you could have Cognito integration or integrations with DynamoDB to create custom auth solution as an example. And I got Amazon Fraud Detector on the bottom right. I'm not going to get into the details of it, but I'll leave you with a food for thought. It's a fully managed service which has fraud detection models built in that enable our customers to identify potentially fraudulent activities and catch online fraud much faster. So some of the use cases are going to be like, for example, those account registrations, like are fake accounts being created, like on those dating apps. It cripples the value of the business if that happens. Identifying suspicious payments online. So you can reduce the fraud by flagging the suspicious payments before you actually process the payments and fulfill the orders. And there's some exciting development happening in this space, so keep an eye out. So to recap, I've talked about the many different areas where your application availability can be affected. I hope I've addressed each of the concepts and how you can look at that from your application. And if you look at each of the 4 sections here, I spoke about how AWS builds its services to be resilient and how you can apply these techniques to your application. So spend time looking at your architecture, see where those particular risks are, and if it comes to it, invent new design patterns. And lastly, we encourage you to keep engaged with our training and certification content today. So as you build your skills, consider preparing for one of our 11 AWS certifications to validate your AWS knowledge and skills, building your credibility and confidence. And you can scan one or both of the QR codes on the screen to get started. So that concludes my talk. Thank you very much for listening, and do not hesitate to reach out to me on Twitter. Thank you once again.